Welcome to Toddcast, I believe number 21, as plan to tie off chapter 4 with this. It's going to be structural isomers, also known as constitutional isomers, and kind of that lead into just isomerism in general. Now, we've done conformational isomers, and we talked about gauche versus anti, stagger versus eclipse, one chair in conformation versus another, chair versus boat. Different ways that structures can rotate, twist, fold, a whole bunch of those things like that. So that's a case where it's the exact same molecule rotated in a way or twisted in such a way or folded in such a way that the atoms are not overlapping. They're not in the same position in space. Constitutional isomers, structural isomers, are ones where they also are not in place, but no matter how you rotate them, you cannot get them to be the same structure. So they have different constituents, or if you will, different connectivity. Fancy way of saying the atoms are connected in a different fashion. And so some of the simplest cases of that would be just to move a chlorine down a chain. So for instance, one of the simplest examples I'll do, let's start with propane, 3-carbon fragment. If I put chlorine on carbon number 1, as opposed to chlorine on carbon number 2, and then filled in the remaining H's. So everything here is C3H7Cl. I didn't plan my screen well, but hopefully you get the point. These would be considered structural isomers or constitutional isomers. They have different connectivity. One would be called 1-chloropropane. The second would be called 2-chloropropane. So it ends up that it's going to be kind of a neat little shortcut that we can take if we want to know if something's a constitutional or structural isomer, name it. And if two compounds have the same name or identical, if they have different IUPAC names, different connectivity in the name, then they are constitutional or structural isomers. Okay, I'm going to erase my picture and dedicate the rest of this to pretty computer-generated pictures. But they have the same atoms, but they are connected differently, different bonds. So what we're going to actually do is use this to try to figure out different possible structural isomers. So one of the common questions in organic chemistry is, given a certain formula, how many different connectivities, how many different possibilities are there for connecting those atoms? In other words, how many different stereoisomers or structural isomers, excuse me. So I'm going to start with the formula C5H10 plus 2. So I want to reiterate what I just did. I have C5H2 times 5 plus 2. So this is what we dealt with a couple videos ago. We're talking about a saturated hydrocarbon. So a saturated alkane, aliphatic, no rings, fully saturated, has a maximum number of H's. If you recall, just let me write this again. We consider CH2s in the middle, some number n, with an H at each end. So what I've drawn is, in essence, this. Let's do these 5. Each of these 5 interior carbons. I call them interior because I'm going to put H's at the end. This would be case where my H is equal to 5, and then I'm going to dangle 2 terminal H's off the end. So this would be H, CH2, 5, H. So again, this C5H10 plus 2, which is C5H12, it's a fully saturated with hydrogen compound. So again, whenever I say the word saturated, I want you to just reflexively say with hydrogen. So it has a maximum number of hydrogens you can have. So we've done some of the work already. Now I want to look at how we figure out how many possible constitutional isomers there are for C5H10. So the question I'm about to answer is, how many constitutional isomers can we get for a given formula? So for C5H10, want to consider the fact that you can put all 5 carbons in a line just like we just did. So the longest chain So the one I just did where I put the H's. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's plus the two terminal ones. So that's my longest chain. But what I can also do is reduce the chain by 1. So basically consider, instead of 5 carbons, 4, and use the extra carbon as a methyl. So this one here, I'm going to attach a different spot, like right there. So my longest chain, instead of being 1, 2, 3, 4, 5, is now 1, 2, 3, 4, and a methyl. So let me fill in the H's here, just to make sure I'm doing it right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's the same thing, but I'm not going to worry about the H's. Just like I didn't draw them here, not going to draw them there, and I'm going to just assume the H's are written in. So now that I've written them in, time for me to completely erase them all. Okay, so no more writing of H's for the rest of this slide at least. But that means I have 2 so far. I have the one that is 5 carbons long, then I look at 4. I cannot put a methyl on number 1. So for instance, if I did 4 carbons in a row, I said, let's put it here, then my longest chain is 5, and that's the same thing I just did up there. So when you add a methyl, it has to be added internal, not at the end. So that connection won't work. But if I put it right here, like I did in this case, again, let's do our IUPAC test. This is pentane, 5 carbons long, so N-pentane. This is 4 carbons long, so it's a butane with a methyl. So we just made 2-methyl-butane. Okay, let me get rid of that drawing because we're happy with that one. Let me try it this way as well. So I have this structure right here. Looks pretty good, I think. 4 carbons with a methyl off. I'm going to leave it for now, and I'm going to do one more. So again, I have terminal carbons here I can't add them to, but I have 2 internal carbons, which I've added them to. And then I've done my 5 carbon chain, my 4, so I'm going to try a 3 carbon chain. And again, I can't add anything to the terminal ones, the first and last carbons, because if I do that, I extend the chain. So I'm going to put both here. So just to make sure I've done this right, 3 H's, 3 H's, 3 H's, 3 H's. So C4, 5, H3, 6, 9, 12, check. Okay, I have made a mistake, and hopefully you're looking at it saying, wait, you made a mistake. Which of course I can't hear you because I'm making a video long before you're actually watching it. But let's say we have this time travel thing, you were able to successfully tell me that this is exactly equal to this. I'm going to say, I don't believe you, let's number it. So I'm going to eliminate any identical structures I've done, just double check. And again, look for IUPAC name. So I'm going to make this carbon chain 1, 2, 3, 4, and put a methyl here. So this would be 2-methyl butane, as we mentioned before. And this is 1, 2, 3, 4, so butane, and 3-methyl butane. But I've done something wrong. The substituent, in this case, the methyl group, has to be on the lowest possible carbon in our numbering scheme. So 1, 2, 3, 4 puts it on 3, but if I numbered the other way, so let's reverse this numbering. So now it's 1, 2, 3, 4. The methyl is now on 2. So if I name this one over here again, this is 2-methyl butane. This is also 2-methyl butane, which means that is not possible. They're one and the same. So we have 1, 2, 3 constitutional or structural isomers for the formula C5H12. This is a ton of work, and being pragmatic, kind of thing that if I make it too long, if I said write all the possible structural isomers for C80, H162, you should probably just, I don't know, write that one off and go on all the rest questions, get those right, because you would not be able to finish writing all those during the test. Can't do that. That's just way unrealistic. But I could viably go to maybe C6H14 or C7H16. That's starting to push it a little bit, but still things within the realm of possible. So one of the homework questions you should do, whether it's formally a homework question or just a suggestion, write it for C3, H8, C4, H10, C5, H12, C6, H14, and C7, H16, all the way up to C7. See how many you get. You'll see a pattern where it sort of grows 1 to 2 to 3. Then it doesn't just jump to 4. You go up even more for C6, and for C7, you have a wider range, but it's still the same pattern. Longest chain -1, where you put the methyl wherever you can. Longest chain -2, where you put 2 methyls on there, never on the terminal end, and you follow this routine. And honestly, it's kind of fun. It's like a game. So I'm going to take the same thing, this constitutional isomers applied to alkanes, and again, we're talking saturated, i.e. linear, saturated alkanes known as aliphatic, and I'm going to apply it to alkenes. So if you recall, the alkene is just like the alkane, except in order to form a double bond, so again, let me just consider 3 carbons here. That's my C3H8. But if I want to make an alkene, I have to have 2 less hydrogens. So I'm going to get rid of 1, 2 hydrogens there and put a double bond in there. So now it's CnH2n for a linear hydrocarbon that has 1 double bond in it. And again, I chose a really simple case because the double bond, if it's not here, it's going to be here, and those are one and the same. Because where the double bond is, that defines carbons 1 and 2. So this is propene, and it's CnH2n, or a C3H6. Okay, so I'm feeling pretty good about this. So now we'll do the same thing we just did for the alkanes for this. So I'm going to do C4H8, and we'll see how it goes, because I'm going to hopefully come up with the same set of rules. We'll see. C4H8, consider the carbon backbone. So just like before, start with the longest chain. 1, 2, 3, 4. Only now, I'm going to also have to place an alkene. So there's only going to be 2 possible chains. 4 and 3, where it's on a middle one. Can't put it on a terminal one because that extends a chain. So there's only 2 longest chains, or 2 chains, excuse me, the longest one of 4, and then the 3. But now I want to place a double bond. So I'm going to get rid of that. I'm ahead of myself here. Oops. So placing double bond, it could be between carbons 1 and 2. It could be between 2 and 3. And it could be between 3 and 4, I think. But let's name it. So always the lowest set of numbers. 1, 2, 3, 4. So this will be 1 butene. Perfect. 1, 2, 3, 4. So this will be 2 butene, because the double bond starts at 2. And this one will be 1, 2, 3, 4, 3 butene, or have I done it wrong? Again, hopefully you're sitting there, no, lowest numbers on that side. So you would tell me 1, 2, 3, 4. I've made 1 butene, meaning this one, same thing as the first one. So only 2 butenes. So I'm going to get rid of these. I'm going to get rid of everything I've written. So there's 2 longest chain ones, the one terminal and the internal double bonds. And then I want to consider the shorter chain. So again, the same thing I mentioned before, 3 carbons in a row and 1 off to the side. And then so it doesn't matter where you put it, it's always going to involve the terminal carbon and the middle carbon, terminal middle, so they'd all be the same. They would all be 2-methyl propene. And I don't necessarily have to say the 1 propene, because it is 3 carbons long, and no matter what, double bond is going to be defined as being at a carbon 1. But hopefully it seems fine. So I'm going to tell you there were 3, and it ends up I'm right, sort of. So there are 3 constitutional isomers, but there's also a different thing we're going to slowly transition to called stereoisomers. So stereoisomers, we're going to typically automatically zero in on things that have same bonds, but different arrangement in space. And we're going to usually think of a carbon with 4 different things attached to it, arranged in almost a right-handed versus left-handed situation. That's going to be the most common thing we look at in OChem. But there's also the double bond. So I can have the double bond in the middle, and they can form 2 different geometrical isomers. So geometrical isomers are a subgroup of stereoisomers, which are going to be separate. So these names are getting really confusing, I understand, but right now constitutional isomers are these 1, 2, and 3. But if I said how many possible isomers are there, then you also have to consider how things can be aligned. So on this first example, 2 H's there, an H and an ethyl. Can't really do much about it. This one is pretty much locked in what it is. But this can have what's known as cis or trans, similar to what we just did with cyclohexane, looking at up, down, as opposed to up, up. So up, up was cis, up, down is trans. Same story here, only with respect to a double bond. So if I have this arrangement where it's H, H, CH3, and CH3, this is known as cis, because they are on the same side. So again, if I draw a line here, same side. You can also get trans, or if they do this. So this would have an H here, CH3, and CH3. So they are on opposite sides. Now we've done this, we've already looked at this, the cis and trans phenomenon, but I do want to revisit it, and also want to notice if you're on the same side, you're cis. So a Z stands for zusammen. It's a German word which means on the same side. So chemists, formerly IUPAC chemists, refer to this as Z, and we'll get into the details of it, but when the highest priority substituent, carbon has a higher atomic number than H, carbon has a higher atomic number than H here as well. So carbon and carbon are your 2 highest priorities on each respective double bond carbon on the same side, so cis. And then famous movie from the 80s, E.T. So E.T., E-trans. So you're on the same side. You're cis. But E.T. was very different. E.T., E-trans. So if they're opposite. So we'll get into those examples if we do geometric isomers, and particularly when we get into the alkenes chapter. So this is sort of foreshadowing. But for this one, there are 1, 2, 3 constitutional isomers. And within one of the constitutional isomers, you also have geometrical isomers. You have a Z and an E. So IUPAC would say Z butene and E butene. Double bond, and I should emphasize this at 2. So specifically, it should be Z2-butene and E2-butene. Okay, this is our first little step into it. So we'll throw more at homework, a few at the problem session, but for now, hopefully that gets you there. But it brought us back to this concept of saturation. When a hydrocarbon is fully saturated, it has 2N plus 2 H's. Every time you add a pi bond or a ring, as we did in start of this chapter, if you have a pi bond, that's 2 less H's, or if you have a ring, that's 2 less H's. So what we can do is take advantage of that to predict structures. So I'm going to start working in the opposite direction. This is the last time I want to work in this forward direction, where we look at a compound and figure out formula. Instead, if I give you a formula and some information, you can deduce what the structure is using this unison saturation. And here's how we'll do it. I want to know what the molecular formula of ergosterol is. So this compound, it's a steroid, nice ring system of 6-member ring, 6-member ring, 6-member ring, and a 5-member ring with hydroxyl here, very minimally water soluble, and an alkyl chain that, depending on how it's shaped, it can send a message when it incorporates into the cell membrane. So you've all explained to me in bio, you learned that cholesterol, very similar structure here, will slide into a cell membrane and change the fluidity. Well, you can also have steroid-based hormones, which also slide in the cell membrane. As this portion slides in, this can actually incorporate in and send a message to the core of the cell to do whatever it needs it to do. Okay, so bio aside, I want to figure out what the formula is. So I have 6 unique carbons here, plus 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So 28 carbons. I'll let you count the oxygens on your own. 1, perfect. And now I need to figure out how many H's. So C28, check. O1, got that. H's, I'm just going to use the rule. There are 2N plus 2 H's in a hydrocarbon. Although this has O, I'm still going to use the same formula. So C28, 28 times 2, 56, plus 2 more would be 58. So I'm going to tell you the formula for this is C28H58O1. And it would be totally true. It would be 2 times the number of carbons plus 2 for the H's if, in fact, it was saturated and aliphatic. It had no rings, no pi bonds. But as it were, that's not quite the case. It actually has 1, 2, 3, 4 rings and 5, 6 for the pi bonds. So for every ring and every pi bond, that's 2 less H's. So this number here is off by 1, 2, 3, 4, 5, 6 times 2. It's off by 12, meaning I've overshot it by 12. So it ends up, it's 6 units in saturation, which means it's too high by 12. So it's actually 46. So this formula is C28H46O. The 1 I don't have to put there. I'm going to get rid of it. And I just want to double check, make sure I've done this right. So let's count the H's. A lot of work, but I will start here. 1, 2, 3, 4, 5, 6. Nothing here. 7, 8, 9. 1 here for 10. 11, 12, 13, 14. Nothing here. 15, 16, 17. 18. I'm going to continue around the ring for 19 and 20, 21, 22. 23 here. 1 here for 24. 25, 26. 27, nothing here, 4 bonds of carbon. 28, 29. So now this little branch over here, so 29, so each would be 30, 31, 32. 1 here for 33. This is a double bond, so 34, 35. 1 here, 36, 37, 8, 9. Methyl 40 through 42, 44 through 46. 43, I should have skipped and counted. But it's numbered perfect. It actually works. Lots of work. So you know what you're thinking? You're thinking there's got to be some formula. There's got to be an easier way. And this is your units on saturation formula. I want you to be able to work with this. So the formula is basically a ripoff of the Honk rule. So to keep a chain going, whatever it is, whatever you want to keep, you must make 2 connections. So if I want to make a chain of green spheres, this is just what I'm going to do. It's one of my things. If I want to do that, every one of these spheres has to be connected twice. Once the one here, once the one here, this middle one here, and one here, so forth, except at the very end, they only have to make 1 each. So you get a little reprieve at the end where you only have to make 1 connection, but everything else has to make 2. So if you want to have a molecule, you want to have a chain of atoms, they have to make 2 bonds each except for the 2 dangling ends. So what we can do is the following. Carbon makes 4 bonds total. So let's say 2 are the mandatory and 2 are extra beyond the mandatory 2 you need to keep everything there. So you need 2 to propagate the chain and 2 extra. So for every carbon, I'm going to say we have 2 extra bonding sites. So every carbon is 2. So 2 times the number of carbons, it's going to help me. It's going to tell me how many extra bonding sites or bonding electrons I have. H, or in the Honk rule, only makes 1 bond. So this one shortchanges you. You need at least 2. Every hydrogen is kind of messing you up because it only makes 1. So for every hydrogen, we say -1. So the number of extra bonding electrons would be 2 for every carbon, -1 for every hydrogen. Honk rule, so I'm only going to consider O and N from this point on. O makes 2 bonds, breaks even. We don't care. Not going to worry about it. And N makes 1, 2, 3. So 2 mandatory, 1 extra. So for every nitrogen, there's a +1. So these are your extra bonding electrons, but I've forgotten about one thing. Again, at the end of every chain, there's an extra H dangling on one side, extra H on the other, or in this case, an extra bonding electron dangling here, an extra bonding electron. So it's 2 times the number of carbons, 1 times the number of nitrogens, minus 1 for hydrogen, plus 2 for the 2 extra bonding electrons. So this number I've just generated here is the number of bonding electrons. These are how many electrons, not counting lone pairs, but the electrons that each atom is using in bonds. Nitrogen is using 1, 2, 3, oxygen 2, hydrogen 1, carbon 4. Every one of those numbers minus 2. So 4 minus the 2 minimum is 2, 3 minus the 2 minimum is 1, 2 minus the 2 minimum is 0, 1 minus the 2 minimum is -1. So these are extra electrons because of the end of the chain. So if you wanted to add in a halogen, for instance, halogens make 1 bond. So you have your requisite 1, just like an H, is going to be short. So if I wanted to, I could also put negative for halogens in the numerator. I'm not going to, but I could if I wanted to. Okay, the last part of it is you need 2 electrons for every bond. So unisaturation represents the number of extra bonds, a pi bond or a ring-forming bond, a ring-forming sigma or a pi bond. So I'm going to take all the number of extra bonding electrons and divide by 2. So you can memorize this formula. There are certain people who do, and they do well in this section. It's all good. Or you can deduce the formula. Just know how many bonds it makes, the honk rule, and subtract 2 from everything. So carbon gets multiplied by 2, nitrogen by 1, oxygen is ignored, H is -1, plus 2 for the end of the chain, divided by 2 electrons per bond, and ta-da, we have the number of extra bonds. So to answer the question, shouldn't there be some sort of formula? The answer is, oh yeah, with an exclamation point. And I think this even earns a smiley face. Okay, so how many unison saturation in this compound? So let's see if I count this right. Double bond, double bond, double bond, double bond, ring. So at first I say 5. And as you're watching the video, I'm curious if anybody disagrees with 5, because this is where we get sort of messed up. So let me go ahead and click what it is. So let's see. Are in fact 1, 2, 3, 4 for the pi bonds, 5 for the ring. Feeling really good. But let's see what happens. Let's see what the answer is. 6. How the heck could that be? And it's because a lot of times we ignore when we write out the formulate for form of some of these functional groups. Alcohol, which is on benzene ring, is actually phenol, ether, and carboxylic acid. So let me go ahead and rewrite this. What this actually is, O2H means it is both an O and an OH. So dang it, there's my 6th. Didn't notice it because it was drawn in a different sort of way. So mess that one up. Oh well. So your job, make sure when it has formulaic features, you pay attention to those things. Okay, so I got tricked on that one, but I now get it. How many units in saturation in this one? 6. So if I want to do the formula, just because I seem to be enjoying that, 6 carbons, 7, 8, 9, 10 carbons. So this will be C10, H22, and 1, 2, 3, 4 O's. Sounds good, except I have 6 units in saturation. 6 times 2 is 12. So minus 12 would be C10, H10O4. Let's see how we did. 3, 4, 5, 6, 7, 8, 9, 10. Formula works. Works in both directions. So let's try a question with it. So how many units in saturation? So let's see how I do. OH, 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 and I'm not going to get fooled this time. So it's pi bonds and rings. 1, 2, 3, 4, 5, 6 pi bonds and 3 rings. So this one seems pretty simple. 1, 2, 3, 4, 5, 6, 7, 8, 9 for the rings. Oh, a real question. Hooray, yippee. Practice makes me happy. So which of the following is most likely to have a benzene ring, or as we have also learned it, an aromatic ring? So I'll emphasize that a benzene ring is an aromatic ring. So aromatic is a general term, but called an aryl ring or an aromatic ring. Benzene. So the benzene is the 6-membered ring with alternating pi bonds. So start by drawing benzene. That's our benzene. And figure out how many units in saturation in benzene. So I have 1 ring plus 1, 2, 3 pi bonds. So this has 4 units of saturation, the ring and the 3 pi bonds. So we need a formula that has at least 4 units of saturation in it. So if I remember right, we do 2 times the number of carbons. We have nitrogen, so I need to add 1 for the nitrogen. We have hydrogen, so it needs to be minus the number of hydrogens, plus 2 for the end of the chain, divided by 2 electrons per bond. So I have my formula. So time to plug in. This is where multiple choice logic comes in. If only one answer can be right, then it's got to be one of the extreme answers, either the one with few carbons and lots of H's, or lots of carbons and few H's. Well, units of saturation, let's see what will work out. More carbons, more units, more H's, less units. So I probably need something that has more carbons and less H's to make the numerator as big as possible, because I got to get it up to 4. So I'm going to start with this answer and see what I get. Answer choice D. 2 times 8 is 16, plus 1 is 17, minus 11 is 6, plus 2 is 8. 8 divided by 2 is 4. I have it. This is the one that has 4. So first answer choice, first consider the C and H ratio like we did. Most units in saturation would be most C's and least H's, which we did, check. And we had a 16, 2 times 8, check. We had minus 11, check. We had a 1, check. We had 2 for the end of the chain. Divided by 2, we end up with 4. We did that. 4 units in saturation. It looks pretty good. It ends up that if you did this one, it'd be minus 13, so it would have been 3. This one would have been minus 13, but also 2 times 7, so 2 less there. And then minus 15. So you actually have, respectively, 1 unit, 2 units, and 3 units. It is worth your time to sit there and calculate the units in saturation for A, B, and C if you want to, or at least for now, take my word for it. So far, so good. So I'm feeling better about this. Here's how we're going to use it down the road. So I've actually messed this one up a little bit. We'll figure out how in a second, and then I'll give you a hint at how it'll show up in the future. But which of the following compounds has molecular formula C7H12O? Okay, so C7H12O, 2 times 7, minus 12, no nitrogens, so who cares? Oxygen we ignore, plus 2 for the end of the chain, divided by 2 electrons per bond. 2 times 7, 14, minus 12 is 2, plus 2 more is 4, so that's 4 over 2. So 2 units on saturation. Okay, so we're looking pretty good. This one has a pi bond and a ring, so it has 2, looking good. This one has a pi bond and a ring. That's not looking good. This one has just the ring, not looking good. This one has a pi bond and a ring, so looking good. So choice A is 2 units, we're good. Choice B, 3 units, it's out. Choice C, 3 units, or 1 unit, it's out. Choice D, 2 units, looking good. Dang it, 2 answer choices left. So this helped me a little bit, got me down from 4 to 2. So now let me just count carbons. I have, for choice A, 1, 2, 3, 4, 5, 6 in a ring, plus 1 there, so C7. This one has 1, 2, 3, 4, 5, plus 2 for the alkene, C7, so that part's good. 1 O, 1 O, so they're both fine, so I got to double check H's. 2, 4, 6, 8, 9, 12. Ah, this one works. So I'm happy with that one. And this one is 1, 2 there, 3, 4, 6, 8, 10, 12. Uh-oh. So it was redundant. Count H's was redundant because if I already know there's 2 units on saturation, I already know that it's 7 times 2 plus 2 would be 16. 2 units in saturation means 4 less H's, so 16 minus 4 would be 12. So anything with 2 units unsaturation and 7 carbons is going to work out. So I can't answer this question. A and D are both correct. So here's what OChem is going to evolve into. This question, I'm going to actually rewrite it as same lead-in part, but now at an IR absorbance of 1714. We haven't covered it yet in OChem lab. We'll get to it when we do spectroscopy, but you did cover this in 121. So I want you to remember that if you have a C double bond O, you have an IR absorbance of around 1700 cm to the minus 1. The odds of you remembering that from lab probably pretty small. But once, hopefully your memory is wetted a little bit and you think back that, oh yeah, that's right, first couple weeks of lab, we did go into that little weird room with whatever compound and try to figure out what we had by looking at the spectra. 1700 was a carbonyl. So that little piece of information, I get rid of choices B and C by unison saturation, by formula, and then I can zero in on this one being the best answer because 1700. Choice D doesn't have a C double bond O, so we can get rid of it. Perfect. Little foreshadowing. You could also learn that a double bond is around 1600. So if this question would have said 1627, for instance, would have zeroed in on that. Or if it had an OH, which none of them do, but if it did, you'd zero in around 33, 34, 3500 or so. So the way we do this is we have to systematically look at all the information here. So the formula helped me to get rid of a couple choices, and the IR helped me to get rid of. So based on the IR, I could have also gotten rid of choice C. So if you just knew the IR fact, you get rid of choices C and D and narrow it down to A and B. If you just know the formula fact, you get rid of C and D and narrow it down to A and D. A is the one that matches both formula and IR absorbance. So this is foreshadowing. We will not get to this till very late in the semester, but hopefully this is kind of detective work stuff that's sort of fun. So the formula, the 2 times every carbon minus 1 for every H plus the number of N's plus 2 divided by 2 electrons per bond, the unison saturation formula, will be awesome for figuring things out, problem solving for down the road. Okay, that's it. Chapter 4 is in the books. I will see you in lecture to go over this, and I'm looking forward to it. It's a, I don't know, kind of a fun section, and it's the one that springboards us into reactivity. So we got one more chapter coming up that'll deal with review from previous classes, and then it'll be on. So I will see you in the next podcast. Bye.